Today we are going to have this presentation on COLAID, which me and team has been working on for the past 2 to 3 years, which is especially for the novel application for accurate detection of the colorectal cancers. Going on to the next thing, the question might arise, like why colorectal cancer in general, while a lot of cancers are prevailing in this community? The reason is simple. We believe that colorectal over here in America, like one of my professors used to say, once you turn 45 or 50 over here, you get the free gift of having a colonoscopy just to have the diagnosis of, risk of developing a colon cancer. And that just imbibes deep in the system that, colorectal cancer can be like subtle in appearance, and we may not find it earlier on in the course as well. It is relatively common, and to be honest, the data is quite like astonishing. Like it mentions that 1 in 20 in this group who's present over here, both male and females, have a lifetime risk of developing a colorectal cancer at one point in their life. The risk factors might differ from each one, maybe diet, genetic, and those things, but 1 in 20, that's the probability over there. And the next thing I would say is like, if you look at the numbers, the incidence, like according to the Cancer Government website, it's more than 150,000 every year and ranks 4th among all the numbers of the leading cancer-related causes in the United States specific. But if you see at the death number, this is the second leading cause of cancer-related deaths in the United States, which is more than a astonishing 50,000 numbers. And as we mentioned, the lifetime risk of male and female, that is another risk factor. Colorectal cancer predominantly involves what we call in simple terms the large intestine, which follows the duodenum, jejunum, ileum, following which the large intestine follows, which is like almost 1.5 meters or 5 feet in length inside the abdomen. Going on to the next thing, so the simple thing, we do a colonoscopy, but how do you diagnose this cancer through a colonoscopy? The answer is simple. Once the doctor puts in the scope, they see the abdomen to check for the colon, any irregularities in it. Once they find any polyps or any irregularities in the mucosal membranes, which is a lining inside the colon, they can take a biopsy from it. The biopsy is then later sent to a pathologist who do this beautiful pink and purple staining, which is called hematosal and eosin stainings, which can depict the structures of the, cellular structures very clearly. If you see in the left, it's the benign, which is like a non-worrisome mass or non-worrisome things, which doesn't have a risk of developing into a cancer in the future. But on the right side, the malignant ones, if you see, it has a lot of purple structures, which we call in the medical terms as the mitotic structures, which is predominantly seen in the cancers rather than a normal cell. So this is how we, the pathologists, like try to classify whether it's a benign or malignant. Going on to the next thing, why would a person would want to develop an innovation or an application predominantly targeting on this? The answer is simple. Even in like all the big institutes and anything, if you ask a pathologist to read a slide, that answer differs from the other pathologists. There is a lot of subjectivity in this issue, a lot of inter-observer variability, which can at times account for 60 to 70% difference. In simple terms, no two pathologists can agree on the same. It's as simple as that. And the other thing is, like, if it's going to be such an issue, finding a good pathologist to read the slides, imagine the scenarios like resource-limited settings, like the rural community hospitals, where resource is really a constraint over there. So we aim to, bring our application and helpful in all these areas. And going on to the next thing, the real-world implication, how would it be helpful? We believe the use of AI, especially in the form of application, which is simple to use by everyone, can help with the interpretation of the slides, reduce the errors in reading the slides, and also democratize the access to high quality care. How? Say a person from rural place can have access to a high quality care if they just have connection to the internet and the image and the modality that we use. Going on to the next thing would be like, when all this sounds lovey and dovey, there is also some limitations to AI that we have to accept and to move forward from there. Number one would be the computational efficiency. Some require really big computers on setups to set up in big institutes, but is really not possible to have the same scale reproducible in a resource-limited community hospitals. That is a main aim, like to see like what we can do from there. And the generalizability and the scalability, as we discussed, and the real-world impact, which most AI models right now are like struggling with. Because AI models, I believe, they don't fail in the lab. They fail when they have to be put it in the real-world testing in a hospital environment where the people or lives at stake over there. And also the same thing that we discussed, the usability and the resource or limited settings, that is one another thing that we should be taken care of. And the next thing, this is what we've been trying to say from this, like the main reason that we want an AI model or anyone over in this room would be like, it should have a high diagnostic accuracy, it should hit the point straight, and it also should be practically deployable and usable in all the interfaces. So this is one critical step I would say, which is really important, because I believe it should be like able to access every institute and every corner of the world, even in the most rural most places, where a simple internet connection can provide expert level pathological care right in the hand of the phones or internet or like with the devices as well. And the interesting part, why we kept it as an ambition turns into reality. This project, you wouldn't believe, was an idea and an aim by two middle schoolers who were done 3 years back. And I'm also proud to say at this point, and I would like to congratulate and appreciate Rice University for this as well, because one of the students is like one of the Eureka member mentorship students who had the chance to work with the like-minded great people over here who helped her with the initial part of processing this application. So that we would really like to thank Rice University for that, because of which we had the chance to mentor these two great students from here on. And before going into the objectives, I want to give a clearer instruction on the people. And this is our brilliant student, one of our great minds, Mr. Kavin, who has done the technical aspect of it regarding the applications and other thing. And this is our mentor, Dr. Krishnan, who has done with the entire lead of this project overall. And we also want to introduce Mrs. Ramya, which are later in the end, who did like the entire AI scriptures and the AI architectures and all those stuff. And also going on to this thing like, so we see that the main aim of this project was predominantly brought in by Mr. Kavin, who's actually in the high school right now. He is busy taking an exam today, or else he would have been here to present with us and take this thing still more in more depth. The aim is simple, to develop a universal, that's more important, AI-powered application for early detection, accurate classification, and precise therapy response evaluation, especially for colorectal cancers, using predominantly the histopath slides that we mentioned in the previously, the blue-green slides, and also like applicable to diverse populations in the entire world. And this made us develop these three main objectives per se. We developed this as a non-profit organization, and we tend to keep it the same because we want this care to be reaching out every nooks and corner of the world, because ultimately it impacts the patient care in the end. The earlier diagnosis, earlier treatment, earlier resources use of the hospital, financial constraints, everything gets reduced to a lot of significant things just by this one early diagnosis and accurate detection, which in this world with the variability that we discussed within the pathologist is quite difficult. So the first objective that we were planning to do is to evaluate the deep learning architectures on colorectal cancer histopath that we discussed previously, and also to integrate the AI models into a scalable cross-platform application, which is the meaningful thing to be done, because most part of the researchers tend to stop with the diagnosis on product of the AI, but they never make into the actual clinical field. That's the main thing that we wanted to bring this project into life. And the other thing, as we discussed, we wanted it to be universally accessible, say in the likes of someone in Greenland who doesn't just have a small internet connection. We just want them to have the diagnosis right in the hand. Or like having affordable diagnostic solutions to promote and enhance equitable care. Once we bring these things, I believe we can reduce the resource constraints in the hospital as well if this application is able to give expert level care. And this is what we were trying to tell. With the model that we went ahead initially, the main thing that we wanted to go with was a ResNet 18, and we will explain it later on why we chose that. So what it does is it reads the histopath slides, divides them into either benign or malignant in a short time. That's as simple as it gets. But we just didn't use the ResNet alone. We tried 7 different models, architectural models, which have 5 different models in ResNet and 2 different in EfficientNet. But in the end, we chose ResNet 18 for a lot of reasons. And going to the method, like there was a lot of methods, like as we discussed about ResNet 18, to process the data sets which took care of these two amazing people, Dr. Krishnan and his team, we took the data of about 25,000 images which were available in the United States, which we classified into lung cancer and colon cancer, which was involved in the images that we got, out of which 10,000 were the colorectal images, which is predominantly of the colon, out of which 5,000 were benign, 5,000 are malignant. So what we did over here is, we split into 60, 20, 20. We trained 60% of the images for the model and validated 20% of them in external data, predominantly in this one, if you see over here, which has like around 150,000 images, which was the data that we validated it on, and we tested it on the application as well. The main thing is we wanted to standardize and augment to improve the model in general so that it can be practically applicable in real world use. And the performance was also evaluated by independent validation and tested, like how we discussed earlier on. And going on to the schema, though the masterminds of the two high schoolers that we mentioned, this is Kavin and this is Ramya, who are right now having the exam in Carnegie Vanguard School. So this is the thing. So we take the biopsy from the colon, like how we discussed through a colonoscopy or any other procedure. We send it through the histopath slides. The pathologist or anyone usually does this, and they give the stained image back to us. And we rigorously train this AI model to run these images, to learn these images with 60% of the number, which is approximately 6,000 images of benign and malignant colorectal cancers mixed. And we validated 20% and tested 20% over that. And in the end, we put these things into a form of an application which can yield some valuable results. Going on to see, these are the ResNet models that we were discussed earlier on. These are the 7 models, ResNet 18, ResNet 34, 50, 101, 152, and EfficientNets B0 and B1. If you see the graph over there, every graph shows an exceptional accuracy and precision along with the F1 score and recall. But you might ask, amidst all these things, why would you go for a comparatively low, older model, which is ResNet 18? And we do have quite a good reason for it, because ResNet 18 is computationally less demanding, I would say, and less time consuming, and that is clearly depicted in the graph that we are about to show next, which is this one. Yeah. If you see over here, like the model showed like an accuracy of almost 1, but the significant point is we were able to achieve it in an epoch run of less than 2 to 3. Just 2 to 3 epochs, and it already had like 100% accuracy. Almost, not 100, it's more than 98, 99% to be exact. And if you see the losses, there was no loss over time as the epochs were continuously running. That is another important and significant thing that we were really proud of, to be honest. More than us, these two great young minds should be proud of it. And going on to the next thing with the ROC curve and the PRC curve, if you see, they go on a straight line and they almost reach unity of 1, as well as along with the F1 scores, which also reaches the unity of 1. And these are the models that we use. This is the data for the training sets of the 60% images that we use, which is about 6,000 images. It had some excellent accuracy and precision. Once we had from it, we just wanted to test the data on the other 150,000 images which we obtained globally, and we were able to produce the same results over there. And if you see the confusion matrix over there, it's absolutely zero misdiagnosis over there. It was able to find all the malignant ones and all the benign pathological slides of the colorectal cancer clearly each time and every run. And this is the same schema that we were talking about earlier. Till now we saw about the earlier aspects. Next we were jumping into the application part of the thing. That's where the real game starts from there. And if you see, these are the data of the applications, and to due her credit, the application was entirely created by this high schooler Kavin, which we are really proud to mentor him like under our guidance for the past 2 to 3 years since the time of COVID. If you see over here, there were 2 models, EfficientNet and ResNet. We took people might ask, like, why not EfficientNet and ResNet? But the same reason we'll be explaining in the next slide. If you see over here, in the internal validation among the 6,000 images, ResNet showed like almost 99% accuracy, while EfficientNet was showed 92%. These are predominantly in the applications. The previous part were in the websites. And these things over here are the same. When we externally validated, ResNet almost showed 95% in the application in the benign ones and 95% in the malignant ones, whereas EfficientNet was kind of dropping down in the percentages, like when we are trying to externally validate the same. So the question again, EfficientNet is far more superior and far more thing, but why not use EfficientNet and train it more like in a systematic way? And the answer is this. ResNet 18, the blue line, and the efficient 18, the red line, if you see the timing they run, for a single image, they were taking less than a second. For 10 images, they were probably taking like almost 1 to 3 seconds. But when you do the same for 1,000 images, ResNet was able to complete within 30 seconds. Whereas EfficientNet, not too long, just 50 seconds or less, but the same thing with the external validation as well. But the thing is, ResNet is computationally less demanding, so it was also able to produce better results. That's the main reason we went with the ResNet 18 rather than going with the newer versions of EfficientNet or ResNets. And we are coming to the key findings. The EfficientNet and ResNet architectures excelled in all the diagnostic and precision and are reading all the histopath slides. We saw the accuracy was almost 99% every time we ran the system over there. And the COLAID application, like we see that we wanted to, what we achieved was computational speed, accuracy, and establishing itself as a powerful solution which can actually make its breakthrough the clinical practice in real world settings. And the limitations, as we spoke, all AI and all technological advancements have some limitations associated with them. It is for us to encourage them and embrace them to make a better product later on in that. So the first thing, as we discussed earlier, it is the potential bias from like having a universal applicability. But I believe with this system, we'll be able to overcome that. And pending prospective clinical validation, that is, we have the application in hand, but where are we going to use it and test in real world? Whether it's able to reproduce the same. And at the same time, we need the same for multi-institutional data sets, because we need the external validation from all the major institutes to see for themselves how it can change the workflow, clinical workflow, patient care, earlier diagnosis, and whatnot from that. And, and the next thing would be the work in progress, which is like what we expect this current work to be in the future from now on. It's like we are planning to collaborate with physicians worldwide to validate the COLAID applications, like how I collaborated with Dr. Krishnan in the initial stages, right from the beginning to the end. I feel like this is one of the products where the consumer was involved in right from the start till the end. And the other one would be like developing AI integrated devices. To be an example would be like, say you do a colonoscopy and they want to take a biopsy. Imagine an AI software which can give the diagnosis at that point of biopsy itself. That is something really like exciting about the future. And also like enhancing multimodal cancer imaging, not just with colonoscopy, also integrating AI in other radiological fields to help diagnose these colorectal cancers and other cancers far better. And the next one being the same thing as we discussed earlier on, which would be like conducting prospective clinical trials to make sure these applications are like reliable later on. Because even if there is going to make one error and it marks like a benign as a malignant or a malignant as a benign, the question comes, who's going to take responsibility for the AI if the patient gets a misdiagnosis? So that is what we need to be really working on from here on and make it like 100% accurate in the future so that we can practically employ it in the system as well. And this is the amazing team that we were talking about. This is Ramya from the high schooler, and this is Kavin, who also won like an award for the US Naval Force last year for the similar presentation for an extraordinary achievement on this application. And Dr. Krishnan, who is the mastermind and guide behind all of us, and Mr. John Shirani, our other teammate. And this is my team from MUC Lancaster. This is Dr. Raghavan, the program director, Lizette Klein, the program coordinator, and Dr. Khan and Dr. Meghna, our internal medicine residents who are involved in this project right from the data sets and everything right from the beginning.